Okay, let's go. Any questions? So I can go. Okay, so okay, what y'all got to do? Yes.
Can you look at on fall, or I think it's fall, yeah, fall 2018, question 2C?
And you're talking about the final, right?
Yes, sir. Sorry.
All right. Right. So if you just matrix here, that would be me, 3.1.
Yeah. Yeah.
Minus 3.
Yes.
Okay, so the question. The question you asked is 2C, is it diagonalizable? Right? That's what you were curious about.
I think, hold on, I think I might be looking at the. Oh, summer 2018. I'm
Okay.
sorry.
Don't do this one, just for fun.
Fine.
So the question for this one, so what I thought you asked was this one, and 2C asked, is it diagonalizable? Okay, so I'm going to go through this problem anyway because I didn't bother to draw the matrix up here. And the first thing I'm going to say is I cannot tell immediately by looking at it whether or not it's diagonalizable. There is one case that we know of where you can just eyeball it until it's diagonalizable. Do anybody know what that is? Yeah.
Is it upper triangular matrix?
What's that now?
It's an upper triangular matrix.
Well, unfortunately, not every upper triangular matrix is diagonalizable. But for instance, that one's not, as a matter of fact. But you're on the right track. Yeah.
Isn't it like if every eigenvalue gives you a linear independent like vector pertaining to that?
What you've given me is the criteria for it to be diagonalizable, and yes. But do you know of a specific time you just look at the matrix without having to bother to figure out the eigenvalues and the eigenvectors and all that, and you can tell, yes, for sure it's diagonalizable. Yes.
Isn't it lower triangular?
Same problems up now. Yeah.
Identity matrix.
I would have to agree with that. That's certainly diagonal, but certainly more matrices in the identity matrix are diagonalized. Yes.
Is it if it's symmetric?
If it's symmetric, that is correct. If it's symmetric, in fact, not only is it diagonalizable, it is what? It's orthogonally diagonalizable. Is this matrix symmetric?
No.
No. So, okay, I can't just look at this one and tell. I don't know. So I'm going to go through this problem, which, by the way, is problem 2 on the final exam from 2021. The first question about this is find all the eigenvalues for the matrix A. Is A invertible? Okay, so first just find the eigenvalues. Is it invertible? This matrix is not invertible. Yes.
The first row is a multiple.
That's right. First row and the last row are multiples of each other. That's something that I just kind of noticed quickly. No way, I already know the answer to this. It's not invertible. So because of that, what do you expect one of the eigenvalues to be? 0. At least one of the eigenvalues has to be 0, just from that observation, right? Well, let's go through it. Let's just get on our horse and ride. So if I were to try to figure out if this thing is, well, it has to be the eigenvalues. Let's see what we got here. So let's do the characteristic polynomial. It should be 3 minus x times this product here. That's going to be x squared. Minus 2 plus 1 is minus x. Right. And that's going to be minus 2 plus 2 is 0. Okay, then this is going to be minus 1. So it's going to be, that's going to be 2x plus 2, plus 2 minus 6. So it's 4. And finally, it's going to be 1. That's going to be minus 2. That's going to be 3x minus 6. Let's see. Actually, that should be minus 2. That's going to be 6 minus 3x. I got the sign instead here. This is minus 2. That's going to be 6 minus 3x. So let's see what we get when this all straightens out. This is 3 minus x times x squared minus x. This is minus x cubed. That's plus x squared plus 3x squared. And this is going to be minus 3x. And this is plus 2x minus 4. And this is plus 4 minus 3x. So get plus 4x squared. This is going to be, see, 4's cancel, and the minus 3x is cancel. It's 2x. And so this is minus x times x squared minus 4x plus 2.
How did the 3x cancel? They're both negative.
They didn't. Yeah. There's 2 of these, not an opposite sign. So this actually should be, let's strike this line here. Let's try this again. This is minus x cubed plus 4x squared minus 6 plus 2 is minus 4x. And indeed, the 4's cancel. There we go. That's much better. This is minus x times x squared minus 4x plus 4, which is minus x times x minus 2 on these squared. So the eigenvalues. Zero and 2. 3. And the eigenvalue 2 has multiplicity 2. Is A invertible? In fact, what's the determinant of A? Yeah.
Isn't it also if you have an eigenvalue 0, it's not there?
Yeah, that's right, because it turns out the determinant is the product of the eigenvalues, right? And so A is not invertible. Determinant of A is 0 times 2 times 2, which is, remember the eigenvalue 2 has multiplicity 2, so, but it's all absorbed from 0. So it's got an eigenvalue of 0, that means it's determinant of 0, so A is not invertible. It says find the eigenvectors corresponding to the eigenvalues found in part A. Okay, so let's do that. Now I'm going to do the 0. Okay, so I haven't done the computation yet. Somebody tell me. Okay, so ultimately the question is this diagonalizable or not, right? So what do I need for this to be diagonalizable? What do I need to find? What needs to happen for me?
You need n linearly independent eigenvectors.
And in this case, n is
3.
three. We need three linearly independent eigenvectors. Without doing the computation yet, what is the smallest number of linearly independent eigenvectors that I can have? Two. Why two?
Because the eigenvalue was multiples to use different eigenvalues.
We've got two different ones, 0 and 2, right? So you've got to have at least two linearly independent. The problem is two going to punk out on us. Two has multiplicity 2, right? And so the eigenvalue 2 will either have one or two linearly independent eigenvectors. If it's got one, it's not diagonalizable. If it's got two, then we're good to go. Let's do the eigenvalue 0 first. Find its eigenvector. Well, that's easy enough because we subtract 0 from everything. So I get the matrix 3, minus 1, 1, minus 2, 2, minus 2, and minus 3, 1, minus 1. And as we noticed at the beginning of the problem, I can turn this into a row of zeros. So I'm going to do this. Let's go. Let's go. So I just left this where it is. I scaled this down to a 1, and I turn this into, well, I just multiply this, or just add this to this to get the row of zeros. And let's see here. Now I'm going to move this to the top, which I probably should have done in the first place. Multiply this by -3 and add it to this. And I'm going to do 0, 2, and this is 1 minus 1 minus 1, 0, 1, 2, 0, 0, 0. And now just straight up add this, and I get 1, 0, 1, 0, 1, 2. That looks like that's my row reduced echelon form. Okay, so let's find our eigenvector. Notice x3 is 3, and by the way, let's play this right now. What it is real quickly. I'm going to start from the bottom because this is a pretty one. I think you're right. This means that x2 is -2 times the first one. And this means this is -1 times that one. Yeah, and that works out nicely. So this corresponds to lambda equals 0. Yes.
You scaled the middle row down. Shouldn't that third one
Yeah.
be positive?
I was gonna say middle row.
That is smart. Yeah, so
Yeah, the one negative one. The third one should be positive.
which one?
The third one.
No, he moved it. One.
Or just in the
minus
top row of
one.
the.
No, you're right. This should be a positive. This should be +1. That's just not my day here. So let's scratch this. This will be a sign change in that final item. Vector. So let's try this again. So this is 1 minus 1, 1. It's got here, but you write a scale to this. Multiply this by -3 and add it to this is 0. 2 times -3 and add it here, it's -2. 1 minus 1, 1, 0, 1, minus 1. And this should be 1, 0, 0, 0, 1 minus 1. So let's try this again. Again, I've got a free variable here. Last one, which is 1. That means this one's the same as that. And this is 0. Let's see, 0, 0, 0. Yes, and this is, I can see that this is, if I take this vector times this original matrix here, multiply this by this, you get the 0 matrix, which is, or you get the 0 vector, which is good. So it's working constant. 0. Now let's do the eigenvalue 2. Okay. So let's do the eigenvalue 2. So basically subtract 2 off this diagonal here. So this is 1. This is going to be 0. This is going to be minus 3. Everybody agree with this? Okay, so this is for language 2. So I'm gonna do this 1 minus 1, 1 times 2 and add it here. It's 2 and add. It's 2 and add. And multiply about 3 and add here. Minus 2. 3. 3. 3 and add here. Yeah. Notice that I can now turn this into a row of zeros and this into a 1. Right. And now it's add this to this because the row reduced echelon form. Now, that should be the row reduced echelon form. Notice that 2 was my crucial eigenvalue, right? I needed 2 linearly independent eigenvectors for this to be diagonalizable, and I need and if there's just one, it's not. So what do y'all think here? What does it look like? Right. How many free variables do you have here? You got one free variable. The number of free variables should be the number of parameters needed. So the number of free variables is actually the number of linearly independent eigenvalues or eigenvectors when you do this computation, right? So it looks like it's not diagonalizable. For this one, I get lambda equals 2. I get, let's see, that's free, middle term is 0. Like that. And okay, any questions on yes?
I feel like every time we do one of these, or like where we try to find if it's diagonalizable and we get an eigenvector or an eigenvalue with a multiplicity of 2, it's never diagonalizable. When, like, what's an example of if we have a multiplicity 2 eigenvalue and it is diagonalizable?
Sure. Okay, so this is simple computation, but it's part of what we're doing. If you do the eigenvalue equation here, you're going to get x minus 3 squared, right? This has a double eigenvalue. Same value, right? Yeah. Now, when you subtract, You had two free variables, right? Basically, x2 and x1 are both free. So what this says is actually in this case, every vector is an eigenvector. That's right. Okay,
Yeah.
right.
So
So
that means it's diagonalizable.
what's that?
So that means it's diagonalizable.
Yes, and of course it should be, because it's diagonal. Perfect.
Okay.
Um,
Would that work for a 3x3 matrix? Or would it have to be like 3 on the diagonal, so then 0 everywhere?
yes, because let me point out something. So suppose you have. This is why if you do a 2x2 matrix, you don't have any interesting examples. And I'll show you one, and I'll show you how to build it. But let me point out something. Suppose A is just any 2x2 matrix you want, right? Just suppose A has eigenvalue lambda of multiplicity 2. And suppose A is diagonalizable. Eigenvectors. We're fixing to actually kind of prove the theory, just kind of through the conversation. So this is kind of what you were hoping for, right? What happens if because his complaint was, well, I've never seen any of these. Well, you're not going to see any for 2x2 that aren't silly, like the one I did in the following sense. So what does this mean? I don't care what A looks like. It means that A is P, D, P inverse, right? Where P is some invertible matrix. Now, tell me what D has to look like under our assumptions here. That is correct. So D has to look like this. Because it's diagonalizable, and I have both lambda and lambda be correct. Now, notice that I can pull this lambda out in front of everything. Right? I can pull this lambda out and then put it up front, right? Everybody agree with me? Well, what is P times the identity matrix? This is P inverse. Now what's P times P inverse? It's the identity matrix. That means your A has to already be diagonal. Right? That's why you don't see any interesting 2x2 examples that are diagonal. Because if you have a matrix that has a double eigenvalue and it's 2x2 and it's diagonalizable, it's already diagonal. But let's suppose that you wanted to make something more. And by the way, this shows you how I make up stuff. Suppose I wanted to come up with a test problem for you guys, right? So this will probably explain what something's going on. Suppose I wanted to say, okay, I want to have, because, you so upset me in the review session, I'm brokenhearted that you've never seen any of these, right? Because it's a cool thing. Suppose I wanted to build one. Let's say with eigenvalues 2 and 1, like this. So I'm going to make a test problem that's diagonalizable this. Now, I have great faith in your abilities to do this class, right? So I'm just not going to say, write this matrix down on the test, say, is that diagonalizable? Because you'll go, duh, it's diagonal, right? So I've got to make it look a little bit more exotic. How can I muck with this and make it look not diagonal anymore? Yeah, but 17, right? Well, probably not diagonal anymore, but it's probably death on a hot plate. Yes.
Find some invertible matrix and multiply it by that and scissors.
Yes, that's what I want to do, right? Put an invertible matrix in something inverse on both sides of it, right? So scramble it. What's the problem practically with that, though? It's a pain in my butt, right? Because, and literally this is what I do. I don't want to just make up some matrix. It may not be invertible, and the inverse might be a terrible fraction, right? Right, or the determinant might be 27, and then I'll have its inverse as a bunch of crap over 27. Let me show you what I'll do. Now, I'm building an upper triangular matrix here, right? I can already tell, even though I haven't finished it, that it's invertible, right? Because what's the determinant of this? And I made the determinant 1 as well, because if the determinant were 2, I might have fractions with 2 in them. Determinant were 27, I might have fractions with 27 in them. I'm gonna only have fractions, everything's gonna be an integer here. So let me make up some stuff, and let me make it small so it doesn't get all out of hand. Something like this. Now I've got to put its inverse over here. What is the inverse going to look like? It's also going to be upper triangular, right? And in fact, it's got to have the inverses. It's got to match like that. So let's see if I can figure out what this is. Bottom row gives you everything you want. Take the identity. This is good. This is good. And this should be -2. Right, because this row times this column should be 0. This row times this column should be 1, and this row times this column should be 0. It doesn't matter what's up here because that's 0. And finally, finish it off here. This row times this column is a 1. Everything else needs to be 0, so it's going to be -1. So that should work. And finally, that's going to be 2, 3. So it's going to be -3. Okay, so you can check the last one. -3. There you go. Now let's see what this looks like when I multiply this out. And actually, that's an easy way to get an invertible 3x3 matrix. Let's do an upper triangle. It might not scramble it to my satisfaction, but let's see what happens. Let's multiply this out. See, I'm going to do 2, -2, 1. I'm going to go 0, 2, 0, 2, 2, and finally we'll get 0, 0, 1. Times the inverse. And we'll see what we get here. This is going to be 2. That's going to be 0. That is going to be -6 plus 4, which is -2 plus 1 plus 1, looks like. This is going to be 0, 2, and -3. Oh, this is -2. -4, right? And 0, 0. Now that's a little bit scrambled, but it's still upper triangular, right? That shouldn't be a surprise, right? Because all 3 of these matrices, this is upper triangle. What if I wanted to make it worse? Right? What if I wanted to scramble it even more? Maybe I don't like this because the eigenvalues are on the diagonal. How can I scramble it more? Do it again, but if I do it again with an upper triangular matrix, it's going to do it with a lower triangular matrix now, right? So what do we get? 2, 0, -1, 0, 2, -2, 0, 0, 1. Now hit this up with a lower triangular. Let's make this more exotic. So the inverse of this should be, this should also be lower triangular. Notice again the determinant's 1. So let's see what we get here. This one's taken care of, 1, 0, 0. So 0. So gotta get 0 here. So that's going to be -1. So this should be -1 as well. And finally, it's going to be 2, I guess, and this is going to be 1. We check that real quick. Works. That is minus 1 plus 1. 1 works. That means just add up 0, 0. 1. And let's see what we get here. When I multiply those first two, I get minus 1, 0, 1, or I'm sorry, yeah, minus 2, 0, 1. I get 2 minus 2. That's going to be 1, or that's going to be minus 1 plus 2, it's 1. And this is going to be 2, 2. Yes. So let's just use that. 2, 2, minus 2. Yeah. So let's see what this final framework is. This is going to be plus 2 is plus 4. This is going to be 1. This is going to be 0, 1. This is going to be minus 2 plus 2 is 0 plus 2 is 2. This is going to be plus 2 plus 3. And this is going to be 1. And finally, this is going to be minus 4, minus another 4. Yes. 2, 4. Yes, that is going to be minus 2, minus 2. And it's going to be minus 2. That right there should be diagonalizable, assuming that I didn't make any mistakes along the way. It should be diagonalizable, and that should be what time. You want to do it, or do you want to try it yourself?
I'll try it myself.
Yeah, so if you go through this, you should get, assuming that I didn't make any mistakes, you should get an eigenvalue of 1, an eigenvalue of 2, a multiplicity 2, and you should find that corresponding to the eigenvalue 2, you get 2 linearly independent eigenvectors.
But so whenever you, this is where I'm getting confused. So you have the two of your eigenvalues are the exact same.
Uh-huh.
And then whenever you plug them in to the matrix, how are you getting two different eigenvectors out of it?
So what will happen is, you want to go just as far as to do the
Sure,
eigen.
yeah.
Yeah, so let's do this. Now, I'll put this matrix over here. So the original matrix is 2, 0, 0, 0, 0, 0, 0. All right, so I am going to assume that an eigenvalue of this is 2 is to not go through and multiply this polynomial. Now we're going to see really quickly if I at least partially did this right. And here's the part of the review session that scares me, because it's, you know, if I make one slip, it's all done. How can I test this?
Just plug in the eigenvalues and reduce this.
There you go. If I get a matrix that's not singular, right? If I get 3 pivot columns, I know I did it wrong, right? Because I did this right. So let's assume that 2 is an eigenvalue. Subtract that from the diagonal, and I get 2, 1, 1, and then I get 2, and 1. Ooh, good sign, right? Because that means when I subtract the 2, I already know that it's singular. And when I subtract 2, I get minus 8, minus 4, minus 4. Oh, that's a smoking good sign. All right. So indeed, 2 is an eigenvalue, because when I subtract it from the diagonal, I get this. What can you say about all 3 of those rows?
They're all multiples.
They're all multiples of the first row. Do I agree with that? So there's a bloodbath going on here. When I look at the null space for this, I get this thing. How many free variables I got? 2 free variables. That means I have 2 linearly independent eigenvectors corresponding to the eigenvalue 2. So I must be living wholesome life because it worked out for me. So let me show you where these come from and why the 2 free variables corresponding to it. Everybody agreed that x2 and x3 are free, right? So that means that the eigenvector, this top equation is 2x1 plus x2 plus x3 is 0, right? And so I can rewrite that as x1 is minus 1/2 x2 minus 1/2 x3. Agreed? So if I were to do this thing, it would look like x3, x2, and then it's minus 1/2 x2 minus 1/2 x3. And so I can rewrite this alike as x3, well, it's 2 more, x2 times minus 1/2 and here are your 2. Okay. You see where that comes from?
Yeah, I get that now.
Any questions? So, at very long last, would you like me to attempt to answer your question in the first place? Let's see, which one was it? It was,
It was on, the summer 2018, to C.
oh, okay, so this is a kind of a nice exercise to go through. So I've got one of these things where I talk about row space and column space and all this business. Okay, fine. Okay, so let me just write the matrix up here. One, two, one, nine. Um, 2, 2, 2, 111. 2, 2. 2, 1, 2, 1, 6. Okay, so this matrix is given to us in this problem. I did get the problem, didn't I? Okay. Find a basis for the column space of A. Okay, so what do we do with this? Yes, yes.
You just row reduce it and then find where the pivots are and then, you relate it back to the original matrix.
Right, right. So this is something that we keep doing over and over again, right? When we find null spaces, all this. I mean, just when all else fails, just row reduce the crap out of something, right? So let's do that here. So let's row reduce. So let's see. First thing I did, okay, I will focus on this 1 here. So like ones, 1, 2, 1, 1, 9. I'm gonna multiply the -2 and add it here. So that's gonna be 0, minus 2, 0, minus 1, 7, yes, minus 7. Two. Yeah, if you guys catch me making a mistake, be sure and give me a holler. We'll mess this up. It looks like the second row is that. And it looks like following the same tack here, times -2 and add. That's going to be -3, 0 again, -2. Oh. 0, -3, 0, -1. minus 2.5, and I guess minus 10. Okay, okay, so I tell you what else I'm gonna do. I'll take a little baby step. I mean, I could divide out and all this kind of business, right? I could divide out by 2 or divide out by 3. I'd rather not, because I don't want to introduce fractions, but I don't have to. And I think this one extra step is going to be worth it. I'm just going to 0 minus 1 minus 7. I'm just going to multiply by -1 and add it here. Well, actually, I will multiply this by negative. Yeah, I will. I'll multiply this by -1 add it here. 0 minus 1, 0, 0 minus 3. That was nice. Y'all see what I did? Just have -1 this, minus 1 this, minus 1 this. By the way, what's the really supposed to purpose of this is? That's exactly right. That's always my purpose, is to make it easier. Because now I've got a 1, right, which I don't have to do fractions. So let me write this matrix. I'm just going to do a copy job here and pick up where I left off. 1, 2, 1, 1, 9. If you want to use fractions, that's up to you. That's fine. Actually, I am. 1, 0, 0, 3 and 2, 0, 0, 2, 0, 1, 7. So I got rid of some signs here. Now conveniently I can use this 1 to sweep out everything above and below it and see what turns out there. So this is going to stay the same. 0, 1, 0, 0, 3. I'm going to kill this business above it. Multiplying by -2 and add, that's still the 1, so the 1 comes -2 and add is 3. And I'm going to multiply by -2 and add below. So it's going to be 0, 0, 0, 1, 1. Okay, so fun. And by the way, I guess at this point is the first time I guess it's been completely clear. Can anybody tell me now? So what we're looking for first is the column space of A. Anybody tell me how to get there? That's right. It corresponds to the pivot rows of what? The original. Good, good. I'm going to take this one more step to get it to row reduced echelon form. That maybe it helped us. But so I'm going to 0, 0, 0, 1, 1. I don't need to do anything to the row above it. But I do need to take this out. So this is going to be 1, 0, 1, 0, 2. So there it is in row reduced echelon form. Agreed? So let's kind of collect the answer here. Basis for column A, that should be the first, second, and fourth columns in the original matrix, right? So 1, 2, and 4. So it looks like a basis for column A should be 1, 2, 2. Second column 2, 2, 1, and fourth column 1, 1. Everybody okay with this? Okay, so we've totally triumphed over the first one. Let's see what happens next. find a basis for the row space of A. And how about that?
Is the same as a null space?
Not quite. Because, the null space is going to be important, but it's not for the row space. Can anybody look at this? I've got a row in this section on form, give it to them what the basis for the row space is.
Isn't that each row that has a pivot? So
That is exactly right. Each row that has a pivot. And this one you can just take from the matrix that you produce, right? So basis for row space. I hate writing the matrix, the vectors in this form, but just to emphasize, 10102. The vector 0, 1, 0, 0, 3, and the vector 0, 0, 0, 1, 1. That ought to do it. What's a good gut check at this stage, do you think? Something that lets you know that, maybe I didn't get the answer exactly right because I messed up somewhere along the way, but tell me something that lets me know that I'm in the ballpark.
The same number of, like, the set of the vectors has the same number.
That's exactly right. The dimension of the column space is 3, and that's the dimension of the row space. All right, so that's kind of a good gut check. So at least I'm comfortable with maybe I'm on the right track. Yes,
Is that always true?
yes, that's one of our theorems, that the rank of a matrix is equal to the dimension of column space, and that's also equal to the row rank. Right. Notice though, here's kind of a good thing to observe. The basis for the column space has 3 elements in it, right? So is the basis for the row space. The column space is a subspace of what? Yes,
To the subspace of Rn?
and what I want to know is what the n is.
Well, n is 3 here.
There you go. So the column space is actually a subspace of R3. And in fact, in this case, it's all of R3. Why? That is right. Those 3 vectors have to be linearly independent because they're a basis of the column space of A. But if you have 3 linearly independent vectors in R3, you got everything. So another basis for column A in this case is E1, E2, and E3. But of course, we don't know that until we make that observation, right? On the other hand, what is the row space of A is a subspace of what?
R5?
R5, right? You got 5 coordinates here. So there's no way that it turns out the column space is all of R3 here. No way on this God's green earth is this all of R5, right? Because you've only got 3 vectors. It's a proper subspace. Yes.
Wait, so can you explain why the row space dimension is R5 again?
It's not. Row space has dimension 3, but it is a subspace of R5 because it's got 5 coordinates in it.
Okay.
Does that make sense?
So the dimensions 3 in the subspace of R5.
Right. It is a 3-dimensional subspace of a 5-dimensional vector. Everybody okay? Okay, so what else we got on here? Find a basis for row A perp. That's your cue. That's right, Brian, that's your cue. How do we find a basis for row A perp?
Just the null space.
That is exactly right. It's the null space. So. Um, and we find the null space to this, right? And how do we find? So it's convenient that I'm in this reduced form because this makes it easier for me to find the null space. So. Because I'm already in row reduced echelon form, I'm good to go to find the null space. By the way, can somebody look at that matrix and tell me what is the dimension of row 8 part? Okay, and how did you do that? Great tell. Okay, right. Two free variables. That's one way to look at it. So notice that x3, I'm sorry, yes, x3 and x5 are free. And these three things, they give us some equations here. X1 plus x3 plus 2x5 is equal to 0. And x2 plus 3x5 is 0. And x4 plus x5 is 0. And so a typical element null space looks like x5 and x3, and there they are because they're free, right? And we'll see x4 is negative x5, x2 is negative 3x5, and x1, most complicated one, is minus x3 minus 2x5. So basis. Can somebody look at that and get that out? So one basis, let's see, with the x3, I'm gonna have -1, 0, 1, 0, 0. And the other one is going to be -2, -3, 0, -1. Everybody agree with me? And this is the null space for the original matrix A, but notice that this is, what's this got to do with row A perp? Notice when you take row times either one of these columns, you get 0, right? So for example, if you take this times this, you're going to get -1 plus 1 is 0. If you take this row times this column, it's going to be -2, 0, plus 2, 0. Same with the original columns too, because it's more complicated. But if you have -1 plus 1, you get 0, -1 plus 1, 0, -1 plus 2, 0. And the other one, you're going to get -2, -6, that's going to be -8. And that's going to be -9 plus -0. Basically, when you take the dot product of either of these vectors with any of these rows, you get 0. And that's why it's the perp, right? Because these two vectors are orthogonal to all these rows. That's what it means to be in the null space. Everybody okay? Okay. Notice, what was the dimension of the row space? 3. And what's the dimension of the perp of the row space? 2. Notice that these are both subspaces of R5, right? R5, 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 R5. This is 2-dimensional, that's 3-dimensional. 2 plus 3 is 5. This is not a coincidence. Yes.
So, but the vectors in the basis aren't orthogonal to each other, are they?
That's a good point. These two things are orthogonal to every one of these rows, right? Or every one of these rows, but they're not orthogonal to each other, are they? How could you fix that if you so desired? You could use Graham Schmidt if you like, then you could make them orthogonal. But yes, in the computation when came out, they came out raw and unorthogonal, but you can fix that if you want, right? Fortunately for us all, I don't think I asked you. Okay, so the last one is, suppose you have a linear transformation. Given by T B equals A B. So basically, you take a 5-dimensional vector, call it V, and you multiply it by this matrix A. And what happens when you take this matrix A and multiply it by a 5 vector? What are you going to get?
3 by 1.
That is right. This is 5. This is 3 by 5, and when you multiply it by 5 by 1, you're going to get a 3 by 1. So hence, input 5 vector, output 3 vector, right? And it says, find a basis for the kernel of T. Anybody know what it is?
Kernel's just a null space, so I take those two vectors.
Right. The kernel is just a null space. Kernel of T is just all the crap in R5, all the 5 vectors, such that P times V, which is AV, is equal to the 0 vector. You've really already done this problem. It's just, do you understand what these words mean, right? Because TV equals AV, we've already figured that out. This is just, the question really is find a basis for the null space. That's it. We've already done that. Here it is. Any questions? Yes,
Can you do number 8 on that same exam?
same thing.
Yeah, it's summer 2018.
Okay, so A is an n by n matrix and lambda p is an eigenvalue. Okay, so okay, so I have lambda and v are an eigenvalue, eigenvector pair. Right. Show that if k is a positive integer, then lambda kv is an eigenvalue, eigenvector pair for ak. Eigenvector pair. Right, everybody okay with it? To do this carefully, I mean, in the real world, so to speak, you'd have to use something called induction, but we'll use sort of a sloppy sort of see the pattern type thing here. So what we have here right? Now apply A to both sides of this equation. So this is A squared B equals lambda AV. Right? Well, what's another name for AV? Lambda B. So now I have A squared B is lambda squared B. So now lambda squared B is an eigenvalue, eigenvector pair for A squared. Do it again. And so this is A cubed B equals lambda squared AB equals lambda squared lambda B lambda cubed. Right? And you can keep going forever. And in general, if you have then if you apply A again, so it always works. Actually, I've sort of snuck in something called induction here on you, but you don't have to be super formal about that. Everybody see why that works? Just keep applying A and you just keep getting the next power of the matrix has lambda, the next power of lambda is an eigenvalue. Okay, any questions? Okay, there's another bit to this, and it says, or it asks, show that if P is an invertible matrix and A is. So suppose now. And A equals P inverse. Then lambda P inverse B is an eigenvalue, eigenvector pair for M. Go lambda P inverse B is eigenvalue. Did you get everything taken care of, or is there anything else?
Yes, right.
Okay. So, yeah, if anybody's got to leave to go somewhere, just give me a holler if you're in a hurry, so. Okay. This one, I guess I would just kind of get on my horse and ride here. Let's look at M, E inverse D. Because I did say this has to be the eigenvector, this has to be the eigenvector. So gosh, I hope that this works out for me. What's another way to write? This is, of course, just moving the parentheses a little bit. What's another name for M? Right, MP inverse. Notice, would everybody agree that so that's what I'm going to do. I'm going to replace this with P inverse A. And then don't forget your things. Everybody okay? Replace MP by whatever it is, P inverse A. And this is, well, any ideas on what we're gonna do now? Any ideas?
Can you set that equal to, lambda p inverse b? or-
Okay, so, right, I think you're on the right side, right? All it is move the parentheses again, right? It's amazing what you can get away with that. What's another name for A, B? Lambda B. And of course, lambda is a constant, so I can pull that out in front. So this is lambda. And this is exactly what we want to show, because let's kind of recapture here. We started here. And we ended here. So lambda is the eigenvalue and P inverse B is the eigenvector. Yes.
Can you do number 3 on the fall 21 final?
Yes, I can. Is everybody okay with this? Okay, let's look back at all 21 here. Oh, right. So let A be T be the linear transformation. T be. In standard coordinates. T be equals A B in standard coordinates. Let B be with B1 equal 32. That would be 2 partners. And it says you may assume that B is a basis for R2, but it's pretty, because this is a two-dimensional vector space, it's pretty easy to see, right? Because they're linearly independent. Okay, find a matrix P such that P changes the basis B to standard coordinates. Okay, so part A. This one, I think I can just work it out. Anybody tell me what it is?
It's those same two vectors inside of B.
And here's kind of a gut check. So I'll go kind of do this computation over here. Notice that you have 3, 2, 1, 1. One zero in B coordinates. You know, this just means the first vector B coordinates, which in this case is 3, 2. So it changes 1, 0 to 3, 2. So it takes that first basis element B and tells you what the standard coordinates are. And same with the second, right? And so that's what we got there. Everybody okay with it? Y'all remember how to play change bases. By the way, what would be the matrix? How would you figure out what the matrix is that changes standard B coordinates? Invert that one, right? That's exactly right. And you all remember if you change B coordinates to C coordinates, you remember how that algorithm works in general? Or you, okay, good. So, okay, I got A. So let's see what happens in B. Find the matrix, call it B, that represents T with respect to the basis B. Okay, now this matrix A represents the linear transformation of the standard coordinates, right? There's a number of ways you can do this. I'm going to show you what I think is the easiest. So here's a diagram. This is standard coordinates, and the matrix is A. All right. Input and standard, output, new thing. Everybody okay with that? Now, what we want to do is we want to find what's the matrix at the B in terms of this basis, right? Do I agree with you? Okay, so let me ask you this. What does the matrix P do? It changes B coordinates to standard coordinates, right? So B coordinates to standard coordinates. The matrix P does this little trick here and it changes B coordinates to standard coordinates, right? What matrix changes standard coordinates to B coordinates? Right. And of course, doing P and P inverse just goes back and forth, right? It's the identity matrix. So this all represents the same linear transformation T. This is the matrix A in this basis. There's some other matrix B in this basis. And notice going around the circle should match. So B should be the same thing you get when you going from here to here should be the same thing as going this way. Everybody agree with that? Right? Because here you're just doing the linear transformation in the basis B. Here's what you're doing the other way. Take your coordinates and turn them into standard coordinates. Do the linear transformation, change it back to the original coordinates, right? So it's the same process. So that is P, and then A, and then P inverse to the 5. Everybody understand that little diagram there? By the way, you can set this up and set up equations, but this is quicker because this A is this thing, P is this thing, and the only thing left is the inverse of this, and that's not too bad because this is actually a 2x2 matrix with determinant 1. 1, 3 minus 2 minus 1. 1, 0, 0. Everybody okay with that? And now all you gotta do is multiply these suckers. And you can check it too. If it still takes a little getting used to, you can go home and do this computation if you like, but I get minus 1, 3, 2. And so at the end of the day, I guess what I get is -5, -2, and that is going to be 9 and 4 is 13, and 5. And this whole thing better have determinant 1, because the original A did. That's minus 25 plus 26. It should be that matrix there. Any questions on it? So this should be the matrix that does the same linear transformation in B coordinates. Any questions? Okay. What is the matrix PVP inverse and what should it be? So next question. What should it be? Yeah, it should be A. Is the matrix B diagonalizable? Is it?
Yes.
What do you think?
Well, I mean, isn't that like literally the eigenalization formula?
Yeah, but I mean, I can multiply any matrix by P inverse on one side and P on the other, but doesn't make it diagonal. How many do you think it's diagonalizable? How many do you think it is not diagonal? The youth of America. You need to get out and vote. What's the matter? Let me ask you this: is A diagonalizable? A is not diagonalizable, right? Because can anybody tell really quickly what would you get if you tried to figure out the eigenvalues of this?
You get everything.
You get x squared plus 1. Does x squared plus 1 have any roots? Real roots? No. This is not diagonalizable over R. And B is a conjugate of it, so it can't be diagonalizable either. Let me give you something hardcore. I mean, if you wanted to go that way, I guarantee you, remember, conjugate matrices have the same characteristic polynomial. So even though this is much gnarlier, so this is going to be, look at the determinant for this. This is going to be x squared. Let's see, that's going to be plus 5 minus 5 is 0x minus 25 plus 26, which is x squared plus 1. It has the same characteristic polynomial. This answer is no, it's not diagonalizable because it doesn't have any real eigenvalues. So the no, it's not. Find the matrix for the transformation t squared with respect to any basis. What a mean problem for old Jim to ask, right? Because there are infinitely many bases for R2. So there should be infinitely many answers to this problem. Or should there? What is standard? Matrix for t squared is blank. That is correct. It is a squared. And a squared is equal to, if you multiply that out, it's that. Basically, this linear transformation is just multiplying every vector by -1. What is the matrix of this with respect to any basis? Let's call this M so I don't have to keep writing. actually, let's call it S for square, right? Because it's the square of A. Let me, it doesn't matter what basis you have. This matrix always looks the same. With most matrices that you encounter, with different bases, they may look different. But this one always looks the same because basically it's a scalar matrix. And by a scalar matrix, let me remind you what I mean by that. That is a diagonal matrix that has all the same entries on the diagonal, all the same. Notice, nice one, nice one. Let me prove this to you. This is what this matrix would look like with respect to another basis, right? Because this is how you change the basis. Just like that diagram I had up here. Notice this is P inverse. Minus 1, 0, 0, minus 1. P, which is minus 1, comes P inverse 1, 0, 0, 1. P. I can pull that minus 1 out front. And by the way, this also shows it doesn't matter, it's minus 1, it can be any land that you want, you pull it out front. And this is minus 1, P inverse P, because that's the identity matrix, which is minus 1 times the identity matrix, which is, so it doesn't matter what the basis is, the matrix is always this, because it's a very special matrix. Let's test this theory, shall we? What was the matrix of A or matrix of T with respect to basis B was right? What should the matrix of T squared be in respect to the basis? It should be B squared. Everybody agree? So this row times this column is going to be 25 minus 26 negative 1. That's going to be 10 minus 10 is 0. This row times this column minus 65 plus 65 is 0. And minus 26 plus 25 is negative 1. How about them apples? Just as predicted, the square of that matrix has to also be the same matrix. So the answer to the last one is, even though I said with respect to any basis, it doesn't matter because for this particular example, it's always the same. Okay, any questions on it? Yes, sir.
So in theory, if you're asking this question, it's gonna have to just be a squared, right?
What's that now?
So like, if you were to ask a question of any basis like this, it would, in theory, have to be a specific example like this where they're all that, right?
I don't know. It depends on how angry I am at you, right? I mean, maybe there should be infinitely answers. I mean, what happens is if you have any scalar matrix, so any matrix. Any scalar matrix has the same property. That is to say, it doesn't matter what basis you use. You can use any basis bar you want. That linear transformation will always have the same matrix. Now, even if you're a diagonal matrix and you're not a scalar matrix, this is not necessarily true. So let me give you an example. suppose I've got this matrix right here, right? And suppose that's a matrix in standard. Let's just use that other, that basis. Let's change this basis here. Let's see, I mean the inverse of this again. If you look at this matrix, this is going to be 6, 1, 4, 1. 6, 1, 8, 1. So the matrix in this different basis is going to end up being 4 minus 3, 2, and minus 1. Each of that. You guys still got to turn it to this. Notice that this is of course no longer even a diagonal matrix, right? And so when you have, so I set this up so it's a particular scale. If that t squared had turned out to be something different, then the problem really probably would have had infinitely many answers. So is that, did I get your question? Okay, other questions? Yes.
Exam 3 this semester and part F, 1F.
Did you say 1? Yeah.
Yeah.
Oh, so I'm going to go back to part D on this too. Suppose A is a real 6x6 matrix, and 4 of the eigenvalues are this. Okay, so let me get you some information here. So A. Real 6x6 matrix. And 4 of its eigenvalues are -1, 2, and 3 minus 2i. So there's 4 out of a grand total of 6 complex, right? What are the other, okay, let's go ahead and answer Dave. What are the other 2 eigenvalues? Right, because the complex eigenvalues that are not real come in conjugate pairs. So if I've got, this is a complex that's not real, I've also got to have minus I. And this is a complex that's not real, so I have to have 3 plus 2i. So there are the other 2. Okay. By the way, I'll answer your question in just a minute. I can't resist. What's the determinant of this matrix? I don't know if I asked you that question.
Yeah.
That is correct. So this actually, just giving you these 4 eigenvalues is actually enough to tell you what the determinant is, because these 2 have to be the other eigenvalues. And so the determinant of A is the product of the eigenvalues. So it's -1 times 2 times I times minus I. And 3 minus 2i is 3 plus 2i. Maybe I did ask this question. Anyway, so this is going to be, this bit right here is 1, and this bit right here is 13. And so that's going to be what, minus 26. Right. Now to the question at hand. It says, or it asks, over which fields R or C, if either, is the matrix from D diagonalized. Is the Over R. Is it diagonalizable over R? No way. How do you know? What's the big giveaway? Right. Let me be more precise, not real life. So, no. How about over complex? It is over complex. What's the big giveaway? How did you seem very confident? How did you know?
Oh, well, I don't know. The complex.
Right, but what is it about these that assure you that it's diagonal? Yeah,
There are unique eigenvalues.
they're all different, right? All the eigenvalues are different, so they correspond to linearly independent eigenvectors. So in the complex, you've got 1, 2, 3, 4, 5, 6 different eigenvalues. That'll give you 6 linearly independent eigenvectors. So yes. So 6 linearly independent eigenvectors. Good question. Okay, others. Yes,
Number 5 on fall 21.
oh, is this the one where you gotta find the singular value decompose? Okay, we'll go through that. Okay, so. So I kind of broke this up into 2 parts. The major goal, I think, probably looks like, is to get a singular value decomposition of this. So we have the matrix A. It says find matrices sigma and B in the singular value decomposition. So singular value decomposition. And I guess it's actually V transpose if you need it, but all I care about is the V here. Okay, what do we do first?
You have to multiply A by its transpose,
In what order?
transpose and then
That's correct. That's correct. So what we need to do, of course, to find this one, we need the singular values. And to find this one, we need to orthogonally diagonalize what we get. We will crying out loud, we need a square matrix, right? And so first we look at A transpose A, which in this case is A transpose is 304 times A, which is 304. And what's the size of this?
3 by 3.
1 by 1.
Yes, this is the world's dumbest matrix. Or at least the 25th dumbest matrix. And there you go, right? So right, this becomes so easy that it's hard now. So the first thing we need to do is we need to take our nice little square matrix here, there it is, and find the eigenvalues. Anybody want to guess what the eigenvalue for this is? 25. Lambda equals 25. Right? Because what can you subtract from it to make the determinant 0? The determinant is just the value of the matrix itself, right? So it's 25. Everybody okay? So what's the singular value? Right, so the singular values we need, so this is the easy part of our thing, so finding this sigma should be easy. Well, we need singular value 5. But remember, this matrix has to be the same size as A, right? That sigma has to be the same size as A, so it's got to be a 3-row by 1 column. And so we fill in zeros to make it match. So there's that. Okay, so far. And what about the B? What's that all about? So B is what is needed to orthogonally diagonalize this matrix here. Well, there's only one freaking entry. It's already diagonal, right? I mean, that's it. And so here, check this out. Ooh, I wonder what the transpose of 1 is. Right, but this is a little bit confusing because it's so easy. But this is your V, and it's also your VT. Because it's 1 by 1. So I think I've answered the first one. There's your sigma, there's your V. Everybody okay with this? And we can check this, by the way, when we're done, if you like. So we've got this so far. So everything okay so far. And the last part is to find the U, because remember what we have in this decomposition is my original matrix A should be U sigma D transpose. D transpose and B are the same here. The last part has to find U. And write out the sigma, right? Right. So how are we going to find U? Well, the columns, if you remember the columns of U, well, first of all, U, what's the size of U? I know what size should make it U be? Should be 3 by 3, right? Yeah, 3 by 3, then a 3 by 1, and then the matrix is 1 by 1, right? So this was a little bit, this is why I pull up U separately, because it's a little bit more obnoxious. Well, I need 3 entries. I need 3 vectors here to fill this up, three vectors, right? And we have that UI is 1 over sigma I, A, VI. Unfortunately, we only have 1 VI, right? Because B, in fact, B is just a single column 1, right? So let's see what we have. And of course, we've only got 1 singular value, so no surprise there. A is 304. And V1 is this. So this is this row from this column, this column, there it goes. And so I get it. Not 5, that can be 5. So this should be 3/5, 0. Everybody okay with it? Here's the pain in the butt to finish this problem. I need to find two other columns and I ain't got no other V's to work with. So what do I do? Yeah.
Use Graham Schmidt.
Right, and the first thing I'm gonna have to do is I'm gonna have to, let me expand this to a basis here. So I'm gonna, to use Graham Schmidt, I'm gonna have to get a basis for R3. So I'm gonna go 304. I'd rather not use 3/5 at this point. This will just make my life easier. Now I've got to complete this. So I've got to have, this may be, after I figure this out, everything else should be easy because it should just Graham Schmidt away. But I need 3 linearly independent vectors, right? Any suggestions? And what was the other? You know what, that looks linearly independent to me because yes, something exists, something doesn't, something exists. The multiplier here has to be 0. Now that means this, the multiplier here has to be 0. I agree. This is a linearly independent set. You can put it in matrix, see it's got 3 different columns, whatever you like. And this is my start because I know that I've got to have this. This has got to be part of my basis. So U1, well, actually, let me call it P1 preliminary because this is, I need to then normalize it. This should be V1. And P2, now I'm going to use Graham Schmidt, right? Somebody tell me why Cassie's choice is especially nice. That's right. In fact, we want to be 2 are orthogonal, which is cool. And also, it's a good choice here because these 2 are orthogonal as well. So let's see what happens. So this should be P2 should be 0, 1, 0 should be this one minus inner product D2 with P1, 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 right? And sweet choice because that inner product is 0, so this part is gone. All right, so that's really nice. And you know what else is super sexy about this is the fact that it's already a blink 1 as well. All right, so I'm not going to have to worry about fixing that. Okay, so P3 should be B3. I think this is a good choice as well. B3 inner product with P2. P2, P2, P2 minus P3 enterprise with P1, P1, P1. Okay, so let's see what comes out of that. See what we get. Let's see, B3 and P2, their inner product is 0. So this one is 0. That's nice. So this piece is going to go away. And so all you're left with is this piece, B3, P1, the inner product there is 3, right? P1 inner product with itself is 25. And the vector P1 that I've got to multiply by is 304. So this is 1, this is 25/25 minus 9/25 is 16/25. 0 in the middle, and this is going to be minus 12/25. And if I rescale that, let's get rid of those 25s, divide out by 4, I get 4, 0, minus. So this worked out pretty nicely because it's pretty clear the inner product of these two is 0. And the inner product of these two, it's kind of a setup here, right? So basically, what do I need for my U? The first one is remember, this thing has to be orthonormal, so I've got to normalize all this. So I've got to divide out on the length of this, which is in fact 5, right? Square root of 25. This one already has length 1. And this last one also has length 5. And there's your U, right? We already had the sigma in the V transpose. Any questions? Yes.
Right, that's this, for the top, right there, where 16/25 is. It's 3/25 times 3 things, or am I just misunderstanding?
I'm sorry, was it, so right here, right, so what's the question?
It's 3 times 3, it's actually 16/25.
Yeah, oh, it's 1 minus this.
Oh,
So it's 25/25 minus 9/25, which is 16.
okay, right.
Other questions? Yes, sir.
Could we do number 6 on that one?
Same example. Okay, let's see. Consider the vector space of all continuous functions on the interval from -1 to 1, with inner product given by the interval from -1 to 1. So someone called this vector space something. So this is just like something we might have encountered in calculus. And the inner product of that g of x is equal to the inner from -1 to 1 of f of x times dx, right? So we've seen this kind of stuff before, right? And the question at hand here is, I want to take W's subspace spanned by C spanned by 1 x to the next squared. Find orthogonal basis. That's it. I did say orthonormal. I hope this works out well. Well, we'll see if I meant to say orthogonal or not. We'll see how bad this is. Okay. So here's what I'm going to do. I'm going to call this. I'm going to call this B1 B2 and B3. Just for notation's sake. And I'm going to construct my new orthogonal basis. So there's my first C, just name one. I'm not going to worry about length until later. B2 is going to be B2, my second C, minus the inner product of B2 on B1. Length of B1, B1, B1. Okay, so far, that's part of the management process. So let's start plugging some stuff in. What I need here is do some calculations. If I do B2, B1, this is the integral from -1 to 1 of x times 1, yeah, and that is 0. Convenient, right? Because x is an odd function on a symmetric interval. I'm sure that's why I have the limits like that. That's 0. So this is just B2. How about that? 2/3 of the way there, theoretically. B3 is B3 minus inner product of B3, B2, 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 minus inner product B1, 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 B1. So there's some crap here I need to figure out for sure. So let me collect this. To make this work, I need the inner product of B3 and B2. This is the integral from -1 to 1. B3 is x squared and B2 is x. So that's going to be x cubed dx. Agree? Which is again 0. Convenient. That means that this term is gone and I don't have to bother to figure out B2, B2. Okay, so what else do I need? I need B3 inner product B1, and B1 is 1, and B3 is x squared. So I get 1/3 x cubed, which is 2/3. So that piece is going to be 2/3. And I guess the last thing I need is V1, V1. And that's going to be 2. So let's see what this turns out to be. B3 was x squared. This term is gone. And then I get 2/3 divided by 2 times 1. So there is my orthogonal basis. To make it orthonormal. And I guess at the end of the day, I do need B2 plus B2. No. Inner product of B1 itself is 2. Inner product of B2 with itself is well, that's the same thing that we got with B3, B1, I guess. So this is also 2/3. Right. And I guess the only thing I'll say I need B3 B3, which is the most obnoxious part. So this is -1 to 1 of that squared. So this is x4 minus 2/3 x squared plus 1/9. Yeah. This is 1/5 x5 minus 2/9 x cubed plus 1/9 x. In like 1, it's going to be the minus 1/9, which is 4/4. So it should be 8/4. So my orthonormal basis should be. I'm just gonna go through it here. That's what we got in Graham Schmidt. Right, orthonormal. So to improve this and make them all unit length, we've got to go through and divide everything by the length. And the length of the first one is 2, so it should be 1 over radical 2. That should be x over the square root of 2/3. And it should be x squared minus 1/3 over the square root of 8/5. And please don't. That's it. That's the answer. Any questions on that? All right, other questions? Yes.
Summer 2018, that's question 3.
Is this from the file?
Yeah.
Okay, yeah, this is fine. Good one to go over. So it gives you this these bases, which I guess I'm let's see, what did I use for these bases here? 1 through 12. 102. 2 minus 1, 1. Okay, there's one basis, R3. And the other one is 412. 215. 116. Find the matrix A that transforms the standard I hope I correct myself when I wrote this. I don't know why I put the word standard in there because that just stands for confusion. That must be a typo. I think that what 3A means is transform the basis B to the basis W. Right. So let's just do that. So find matrix. So it's good for us to review You know how to do this? See, does anybody remember how to go about this? Yes.
I remember. I think. I would set, I got each one of the vectors and I set it equal to the other basis row in matrix form. And I row reduced it, like each time. And then I just combine all those vectors together.
Right, yeah, you kind of do this longhand. Do you all remember this where we? W two. Six. The other one's 1 through 12. 102. 2. Y'all remember this? Do you remember how the algorithm works? Right, well, and in fact, the row reduced echelon form should be the identity matrix, if this really is truly a basis. In fact, if you get anything other than the identity matrix, that means I screwed the problem, right? So, let's do that. I'm gonna move this to the top. So I've got to do the same to the other side. So I'll have to move 3 minus 1 to the top. In the second row, I'm going to put what I have here. I'm going to multiply this by -2 and add it here. So I'm going to get 0, 3, 4. And I've got to do the same thing here. So that's going to be 6, 2, and 3. Everybody okay with that? You guys better watch me carefully with this. And in the bottom row, I'm going to multiply this by -4 and add put it in the bottom. So it's going to be 0, -2, -3. And that's going to be -11, 1, and 6. -11, 1, and 6. Yeah. Okay. I'm going to do my same trick here. I'm going to do one with quick line. I'm just going to. I'd really rather not do the fractions. Single 1, 3, 0, -1. So I'm going to go 0, -2, -3, -11, -6. And I'm just going to straight up add this to give you a 1 here. Next 2 ones, -5, 3, 9. Okay. Next, I'm going to multiply the middle by 2 and add the bottom. So one at the same top, 1, 1, 1, and 3, 0, -1, 0, 1, 1. Oh, and you know, actually, I take that back. Because I see something that's going to shortcut my work. Does anybody else see it? Notice I can totally take this out right here, right? Because this is a pair of 1s. So I am going to multiplies by -1 and add above, that gives me a much more convenient top row. And so along the top, that's going to give me 8 minus 3 minus 10. That's right. Multiply this by -2 and add it down here. And that's going to give me, or I'm sorry, not by -2, by 2. And that's going to give me 0, minus 1. It's going to be -21. 7 and 24. Right. Minus 21 and 7. Okay, so I'm gonna take, actually. Let's see. 21 minus 7 minus 24. So I'm gonna change the sign of that. For that, I'm gonna straight up add this. I'm gonna straight up add, I'm gonna get minus 26. 10, 33. And I can just leave the top at home. That should be it. This should be the matrix that changes V coordinates to W coordinates. And if you're really stubborn, then you can use the matrix and show that it takes this to this, this to this, and this to this. Any questions? Oh, and you didn't ask about the second question, so I guess that probably. So if B is the matrix that transforms WB, so A is the matrix. Is the matrix that takes whatever it was, B to W. 8 minus 3, 10. Minus 3 is minus 26, 10, 33, and 21 minus 7 minus 24. What is the matrix? So this matrix takes B coordinates, the B basis, the W basis, B coordinates, W coordinates. What's the matrix? What's the relationship between the matrix that does it reverse?
It's the inverse of that.
That's correct. Nobody wants to find the inverse of that thing, right? It's kind of a mess, but I mean, it's doable. Yeah, it's got terrible numbers in it, right? But you get something good. Okay, what else we got? Yes,
I just have one question about the definition.
yeah.
So if you asked us to define a linear transformation, how do I answer that? Like incorporate it?
Oh, if I ask what is a linear transformation?
Yeah.
Okay,
Like T B to W is
right.
find what it means to be a linear
Yeah, so
transformation.
here, let me write down kind of a full credit response for this. Question. And yes, a constant from vector space D in vector space F such that number one, B of B one plus B two is equal to T of B one plus B two. Two T of CV is CT for all B and B and C. That will be like a perfect response.
Isn't it?
What T of zero equals zero? That is a consequence of that. It follows from this because if you let C be zero, you get T of the zero vector is 0 times this thing, which is 0. So if you put it there, I wouldn't complain, but it's actually a consequence of the other two. Now for subspace, the way we define subspace, I'm glad you brought that up, Mike, especially because S in D is a subset of one zero vector is in S two if let's say U and B are in S. So is speed and three if U is in S and C is in R, then C is okay. Notice you have this extra condition here. You might say, but Jim, you really don't need this because you can just take C to be 0 and you need C U as this. But you actually do need it here. Do you know why? It's subtle. It's very subtle.
So is it empty?
That's very good. That's exactly right. Because I'm proud of you. I'm full of smiley face or something. Yeah. So that's exactly right. You have the zero vector is in S. This guarantees that there's at least something in there. Because the original subset in the worst case scenario could be the empty set, in which case these are both vacuously true. Right. So you actually need this. This is not a concern here because you're already assuming that you have vector spaces, which are not empty in the first place. So yeah, be sure that you write 0 as an S or something like that, or you could say S is not empty. It's got something in it. Yes.
It's more a question number 4, but it's more or less clear. Later. For each eigenvalue of A, find a complete set of linearly independent eigenvectors And the only reason I asked about this one, so it's worth a lot more, and I feel like I'm,
Okay, so maybe you should show this. Oh, it's on the same one. Let me get number 4. Maybe there's more eigenvectors. Let me see. On the eigenvalues. For each eigenvalue, find a complete set of linearly independent. The fact that that's worth 10, I would expect, I suspect you're probably gonna get 2 different eigenvalues, right? That would be my guess, is that I haven't worked the problem out in a while, but. Yes,
For B1B on the final exam from last year, I just want to make sure, 'cause I did it, I just want to make sure this is right. I said, I'll give you a minute to read it.
is this the thing about if it's a linear transformation, then what's the kernel?
Yes. I said the kernel of T is the set of vectors from B that gets mapped to the 0 vector in U.
Yeah, it's a set of vectors in V such that T of V is the 0 vector. Right, that's right. Okay, anything else? Thank you. You're welcome.
not the exams, just last quiz. And
Oh, the last quiz?
it's more, it's not on it, it's just, I just want to know how bad will that affect.
Since you're one of about 10 people in the class and this is the last quiz, probably not so much.
Okay.
Yeah, I don't know what happened with that.
I saw it.
Yeah, I felt really bad because I think it was go through the quiz. It's make sure that you can do it, but I think it's not too bad.
It's pretty,
What's that?
it was pretty,
That wasn't too bad.
not easy, but
It was, but it was get on your horse and ride. You know, you can kind of do it, right? Okay.
The final is cumulative, right?
It is, right. So I'm not going to try to get too obscure on you. And the good news is it's a math class. And so most of the stuff that you've been doing, you know, it's kind of fresh in your mind. I mean, my God, I mean, we row reduced until we're blue in the face, right? So.
We found that out.
You're welcome.
could you? With the Apache-Schwarz inequality, it says for J, says state the Apache-Schwarz inequality.
Cauchy-Schwarz inequality is this. If you have, it has to do with the size of vectors and their inner product. That ring a bell?
Yeah.
The absolute value of the inner product of these two is less than or equal to the size of the product of the sizes.
If we put that, would that be a valid?
What's that now?
If we put that, would that be a valid answer? Or do we have to like?
I would say V and W are vectors. I mean, give me some context, right? I mean, just tell me what this is. Anything else?
For the last one there, it says if using an orthogonal matrix, what is U times U transpose? Wouldn't that just be the identity?
Oh, if it's orthogonal, yeah.
It doesn't matter if it's orthogonal, you multiply U times its transpose, and it's just the identity, right?
That's right. I mean, yeah. So what it means to be orthogonal is its transpose is its inverse. Right. So if it's orthogonal, then when you multiply by the transpose in either direction, you'll get the identity.
Thank you.
You're certainly welcome. You gotta do your best, try to relax and, just, I know this is stupid advice, but try to make it as fun as you can, relax, do your best. I expect you'll have plenty of time. I don't think you'll run out of time.
It's a 2 hours, 30 minutes.
Yeah, the exam period is 11:30 to 2. And the exam that you take will certainly be longer than, the individual midterm exams you've taken. But I mean, if you look at the old ones that I've posted, that'll kind of give you a ballpark for the week, right? More or less. I think that you should be able to finish the exam, check it over and comfortably turn it in before the 2 hour mark.
Okay.
I mean, I've had some people take the file and get done in not too much more than an hour, so. Well, right. The first people that turn in the exam, that's either really good news or really bad news, right?
Yeah.
But the ones that turned it in early, it was good news, so.
Will you be having any office hours between now and exam time?
No and yes. I've got a PhD defense in Austria tomorrow, so. I've got
Austria?
Yeah, Zoom, right.
Oh, okay.
Yeah. So, yeah, so I gotta go catch a plane. And I'll be around maybe. What you should do is just email me or, actually. Let me know my phone number on the internet. Duran, do you have anything?
No, I'm good.
Do you have anything, Duran?
No, I should be fine.
Thank you. No? Okay. All right, have a good one.